So we're going to talk about nonlinear effects on tides. And did you see how it moved? Did you see the animation? Let me see if I can. So what's wrong with that wave? Can you see there's something funny about that wave? You see that sinusoid wave? Not a sinusoid wave. It's being distorted. Or the tide is being rectified. So what we say is that the tide is rectified, in which case the rectification of the tidal current will cause overtides and compound tides. So what do we mean? Okay, here are several examples of what can happen to the tidal wave. So we have a simple sine wave here, and we can approximate the tide coming into the estuary, into an estuary, just outside an estuary, as a simple sine wave. It's very close to a simple sine wave like that. But then inside the estuary, it can get modified. How does it get modified? Well, first of all, it goes into shallower waters. So what happens to the phase speed? It decreases. So if the phase speed decreases, why does it decrease? Because of the square root of GH. It travels at the square root of GH. So if the speed decreases, what happens to the wavelength? To the wavelength of the tidal wave? It also decreases. So it gets deformed right there, but that's not the main effect. You can have friction acting on it, so it makes it dissipate, or you can have that the coastline converges, so it can get amplified with the convergence of the tidal of the coastline, like you read in Friedrich's paper. So what happens there is that it will travel at different speeds, or it will be affected differently during flood than during ebb. So you start to have some asymmetries, as you can see here, and that's what we're going to talk about today. You can see these asymmetries in which this low tide is much longer than the high tide, and it has sort of double peaks, much more pronounced here, double low waters. And then you can have an extreme, the extreme of the distortions is this sudden increase in the tidal elevation, a rapid decrease, but a sudden increase in the tidal elevation, and that's a tidal bore. So notice the big distortion from a sine wave to something that looks like that, in which you have a very sudden increase in the sea level, right here, and that's a tidal bore. So we'll talk about what's responsible for this. Do you have any idea of what's responsible for this? I sort of mentioned it. The nonlinear effects, but physically what happens? Okay, so here's another example of what may happen. This is in the Gironde River in France. Did you like that? How did I do, Amy? Thank you. Yeah, this is a tide at the entrance to the estuary. So that looks pretty much like a sinusoid, right? And you can see the other lines are the tides as you go further into the estuary, all the way to the head of the estuary at Bordeaux. And you can see what you see there. You can read the caption and answer the question, or you can see it here. What happens when the tide goes down? Is it faster than when it goes up? Can you tell? These ticks on the x-axis are approximately 1 hour each. So you can see here that during ebb you have 1, 2, 3, 4, 5, 6, 7, 8. And during flood you have 1, 2, 3, 4, or 5. So you have that the tide goes very slowly down and then rapidly up. Slowly down, rapidly up. Why is that? You think? Notice that at the entrance to the estuary, it's almost symmetric. Same length of time during ebb than during flood. That is going down and going up. What causes this very strong asymmetry in the water elevation going very slowly down and rapidly up? 4 hours faster in the flood than the ebb. It all goes back to the square root of GH. Right? Because during ebb, during this phase, what's happening to the depth of the estuary? It decreases. And during the water coming up, the depth increases. But how is it significant? How can tide be significant in the water column? When would you say that the tidal variation is significant for the water column of the estuary? When will it change the square root of GH? Drew has the answer, but he doesn't want to say it. He wants to say it, but he doesn't want to. So during ebb, what's H? Well, how large is H? H is lower than H during flood, right? But how different do they need to be relative to the water depth for this to be an effect? So for example, if we're in 100 meters of water and the tidal range is tidal amplitude is 1 meter, tidal range is 2 meters. So say during flood, the water column would be 101 meters, and during ebb it'll be 99 meters. Is there much difference between the two velocities? No. How about in Ponce de Leon inlet? Well, let's say the water depth, the mean water depth is, what would you say?
5 or 6 meters.
5 or 6? Okay, let's say 5 meters. That's probably high value, but anyway, let's see what's 5. And let's say that the tidal range is also 2 meters, so the tidal amplitude is 1 meter. That's probably a large value too, but for the sake of argument. So during flood, the water depth, the mean water depth in the estuary is 6 meters, and during ebb it's 4 meters. So what's the square root of 60 versus the square root of 40? So that's how different the speeds will be. Now think of a shallower estuary where you have mean water of 2 meters or 3 meters, and the tidal range is 3 meters. So during low tide you'll have 3 meters, and during high tide you'll have 6 meters. So that's a very dramatic change in the phase speed of the tidal wave. So that's why during flood, in a system where the ratio of the tidal amplitude to the depth is large, eta over h is large. What do I mean by large? Maybe greater than 0.2 at 20%. Where eta over h is large, then the tide will be strongly distorted, right? Because there will be strong asymmetries between the phase speed of the flood and the ebb. Does that make sense? Okay, so it all goes to that, to the phase speed of the tidal curve. So where do these nonlinear effects come from? And I'm going to be referring a lot to a paper by Bruce Parker, and he actually has a book that just published last year, 2007, on tidal hydrodynamics that has all this stuff updated. And that's why I decided to include a few more figures today than I had on the lecture before. So we'll talk about nonlinear interaction. So we'll consider a tide that has a sinusoid. Notice that that's a pure sinusoid. There's no mean flow there, just a symmetric sinusoid. And if we look at one of the nonlinear terms in the momentum equation, that advection term, That advection term can be written like that. Does anybody get upset if we do that? If we rewrite it like that? They're equivalent, right? So notice that we have u squared, and we're going to take that these sub I indices as one harmonic, the M2. So u squared is going to be equal that one times that one. That is the product of two harmonics. And you've probably seen this in your waves class, right? And your nonlinear waves class too. Who has taken nonlinear waves? Nobody? Okay, so you haven't taken this, but but have you seen it in your waves class? Did you see how you generate over harmonics of higher frequency and harmonics of lower frequency than generating frequency? Maybe? Somewhere you must have. Okay, so anyway, we have the product of two sinusoids here, or cosinusoids. So that product is that. So again, this comes from the nonlinear term, from the advective term. So the product gives you a square term, and this gives us, this cosine squared equals 1/2 of 1 plus cosine twice the frequency time. So notice that we have a term with zero frequency and a term with twice the frequency of the generating term. So this zero frequency means that there are no variations in time. So this is a residual. So this would be the residual flow, right? So a nonlinear interaction of the tide with itself will generate a residual flow. That is a mean flow. When you average over the tidal cycle, you'll get this, and you'll get this. What is this? If the period of the M2 is 12.42 hours, what is the period of twice the frequency of the M2? Half the period, which is 6.21, right? 6.21 hours. That's called the M4 over tide. So again, that's explained here. Again, the advective term then is proportional to a residual term that's not a function of time, and a harmonic that has twice the frequency, which is the frequency of the M4. So twice the frequency of the M2 is twice 2 pi over 12.42 hours. So we have 2 pi over 6.21 hours. And that's the frequency of the M4. So that's something that should be in your vocabulary, and in your disk drive, that you know what the M4 is and what the period of the M4 is. I trust that you have the period of the M2 in your hard drive by now, right? In your disk drive. Yes. It is? Of the M2 or the S2? What's the period of the M2? 12.42, and the period of the S2? 12 hours. So if instead of having the M2 here interacting with itself, if we had the S2, what would be the frequency of that? What would be the double frequency of the S2? Would be 2 pi over 6 hours, right? Get the concept. Okay, now that was the M2 interacting with itself. Now if the M2 interacts with another semi-diurnal constituent, then you have here the M2 and the S2. So what you get is the product of the two that multiply the cosine of the addition of the two frequencies plus the cosine of the difference between the two frequencies. So notice that the interaction with one harmonic and another harmonic of different period or frequency will result in a distortion that's of higher frequency. So it's a high frequency distortion. If you add these two frequencies, and I invite you to do it, again in the comfort of your house, if you add these two frequencies, you'll get that the period resulting from the addition of those two frequencies is 6.1 hours. So it's not much different from the twice M2 or twice S2, around 6 hours. So we call that a distortion. the wave gets distorted because it acquires a higher frequency from the interaction. And also, the interaction produces a modulation, like your FM radio, frequency modulation. That's what they do. They modulate different frequencies of radio waves. So what you get is a low frequency modulation. And that, again, I invite you to subtract these two frequencies, M2 minus S2, and you'll get a modulation of 14.8 days. By the way, this difference in frequencies is what gives us a Rayleigh criterion for sampling a time series. Do you remember, have we talked about Rayleigh criterion in this class? Can anybody remind us what Rayleigh criterion is? The Rayleigh criterion is? What is it? Everybody's going. So the Rayleigh criterion is effectively this thing, the modulation produced by two signals, and it's the difference between the two frequencies. So if we want to go to the field and sample and get a representative sample of the tides that gives us the contribution from the M2 and the S2, we need to sample as long as the difference between the two frequencies. So at least we need 14.8 days, 15 days of data to be able to separate the individual contributions from the M2 and S2. So if you get this criterion, how long do we need to sample to separate the effects from the M2 and the N2? Does anybody know? What does the interaction of the M2 and N2 do to the tide throughout a tidal month? Remember, we've talked about strong spring tides and wimpy spring tides, and strong nip tides and wimpy nip tides. Those are called, the asymmetries are caused by the N2, and that's because of the orbit of the moon when it's in perigee and apogee. So anyway, how long do you need a record to be in order to separate these individual effects from N2 and N2? Okay. How many?
28.
Very good. Yeah, did you do it on your calculator, or just it's in your disk drive already? Yeah, so it's almost 28. I think it's 27.8, but practically 28. So that's why you need at least 1 month of data in order to separate the influence of the M2 from the N2. Okay. So here's the difference between the frequency between the M2 and the S2. So again, if you do it, you don't have to do it in the comfort of your home because we're doing it here. If you do it, you get that the difference is 0.0177. And the period, this is in hours, cycles per hour. So in order to convert, per hour, because we have hours here. So in order to convert to days, we divide 2 pi over that difference in frequency, multiply times 24 hours per day, and we have 14.8 days. So in the same way, you can calculate exactly the modulation produced by the M2 and the S2. So remember, that modulation is equivalent to the Rayleigh criterion, and it makes sense. Two waves interacting with each other will produce a modulation of a certain period. And in order to be able to distinguish the contribution from each one of the two harmonics, you need a time series at least as long as that modulation. Right? So keep that in mind. Also put in your disk drive the Rayleigh criterion. It's a very important thing to keep in mind. So these nonlinear interactions arise from the UdUdx or the VdUdy or the WdUdC, or they're all nonlinear terms, the advective terms. But they also arise, these nonlinear interactions arise from bottom friction. And the bottom friction term yields two mechanisms to produce overtides and compound tides, which is the product of the surface elevation times u squared and the u squared. This comes from, you remember the bottom friction term in the momentum equation? When you integrate vertically, the bottom friction term equals drag coefficient, the favorite number of AJs, 2.5 times 10 to minus 3, multiplied times this u times absolute value of u divided by depth. But the depth is the average depth plus the eta. So when you expand that h plus eta in the denominator in a binomial expansion, you get these two terms. That's where it comes from. So you can also get nonlinear interaction from the divergence term in the continuity equation. And that is proportional to the product of eta times u. Eta surface elevation times u plus u. Notice that in all these interactions we get at least meter squared per second, or meter squared per second squared, or meter cubed, in this case, meter cubed per second squared. Here is meter squared per second. So that's why it says that it's nonlinear interactions. So again, this eta u comes from this continuity. This would be the continuity equation that is vertically integrated and also laterally integrated. So B is the width of the estuary. And so from this product, eta times u, that's where you get nonlinear interactions. And that's when the mass converges, say, in an estuary where the coastline converges. That distorts the tidal wave, and that's through this mechanism. So we have four mechanisms that generate nonlinearities. And these are, we said that this comes from the continuity equation, so this is called the continuity mechanism. Then we have the advective, and these two are from the bottom friction. And this is from the fact, this one comes from the fact that at high water, this eta, this product will be much different than on low waters. So this will be this will cause a distortion of the tide also. We'll look into each one of these in a little while. All right, so that's where they come from. And a lot of the symbols have been. Okay, that's all right. Here we have different types of interactions between different harmonics. So this is the cream of the topic. This is what you're going to get when you do a spectral analysis of a signal that has been distorted. You're going to get these types of interactions that we'll discuss right now from this table. So when the M2, which in most places of the world, that's the generating frequency for the tide, when it interacts with other constituents, that interaction, that nonlinear interaction, will generate, as we saw, overtides and compound tides. So we have here, when the M2 interacts with the M2, it generates these, and we'll talk about them in a moment. When the M2 interacts with the N2, it generates these compound tides. When it interacts with the S2, it generates all these compound tides. When it interacts with the diurnal K1, it generates those compound tides. And when it interacts with this other diurnal, it generates all those compound tides. Okay, so let's go step by step. So if you remember, when we showed the cosine squared, how the M2 generates a residual term and a double frequency term. So the residual term here is here, which is the difference between the M2 interacting with itself. So the difference in frequencies equals 0, so that's a residual term. So what it says up here is sigma sub index 2, referring to the M2 tide, minus the frequency of whatever harmonic appears on this column. So again, we're looking at the M2 interacting with itself. It produces a residual and an M4. Right. Now the residual also, the M2 can also produce M6 and M6. And you have the periods of each one. The period of the M4 is 6.2 hours, and the period of the M6 is 4.1 hours. All right. Now, when the M2 interacts with the N2, remember the N2 is caused by the elliptic orbit of the moon. It produces a modulation, that is the difference between the two frequencies, the difference between the frequency of the M2 and the frequency of the N2, produce a modulation with a period of 27.3 days. So that's pretty close to what Drew said, 28 days. 27.3 days is the difference between M2 and N2. There's a period of the N2, if you don't remember it. And then, so that's the modulation. And the distortion will cause a compound type that's called MN4 and has a period of 6.27. Notice that it's very difficult to distinguish between the M4 and the MN4 because they're both 6.2 hours. Right, so they arise from the distortion of the semidiurnal with another semidiurnal. So that's why they're so close to each other. Now we have a further modulation here. Twice the M2, which would be the M4, with the N2 generates a semidiurnal modulation, and then twice the M2 again with the N2 generates these distortions of around 4 hours. So notice that they're very similar to the M6 too. So all these are called 6th diurnals, these are called 4th diurnals. Similar situation with the S2 because it's a semidiurnal. The modulation produced by the M2 and S2 has a period of a fortnight, 14.8 days. So that's what a fortnight is, 14.8 days. The modulation of the M2 with the S2. And a distortion of 6.1 hours. Another 4th diurnal that's very similar to the other 4th diurnals that we have here. And then we have this semidiurnal modulation that's caused from the M4 and the S2, and then these other 4th diurnals. So notice that if there are strong nonlinear interactions among the semidiurnal harmonics, then you're going to have very strong signals in the semidiurnal, not only because the forcing semidiurnal, but also because of the interactions of the high harmonics with the semidiurnal itself will produce a modulation of close to 12 hours, as you see in these two, the 2MN2 and the 2MS2, they're close to 12 hours. So in the semidiurnal band, you're going to have a very strong signal. And also you're going to have a strong signal, as we will see in example, in the 4th diurnal band. Okay? So now, very interestingly now, the interactions of the semidiurnal with the diurnal, they will generate compound tides of new periodicities that we haven't talked about up to here. So notice the M2 with the K1 produces a modulation of pretty close to diurnal, 1.07 days, which is close to those 24 hours of the K1. And a distortion of 8 hours. Notice that also the M4 interacting with the K1 will produce a modulation of 8 hours. So these are 3rd diurnals, 3 times per day, around 8 hours. And then you get these very interesting distortions here of twice the M2, which is the M4, plus the K1 will give you the 2MK5, which has a period close to 5 hours. And then you're going to have something weird, that's 4MK7, so hepta diurnals, so 7 times per day. 7 times per day is 3.57 hours. And that's the interaction of 4 times the M2 minus the K1. So in very strong strongly nonlinear systems where you have the influence of both M2 and K1, you might be able to identify this weird distortion that's close to 3.57 hours. Can you think of an example when this can happen, where this can happen, where the M2 and K1 both contribute to the tidal signal, and you would expect strong nonlinear effects to happen? Can you think of a geographic place where this might happen?
What's the K again?
What's a K1? Can anybody help Matt with K1?
The sun?
The diurnal. The lunar semidiurnal. No, sorry, the solar diurnal. What am I saying? Solar diurnal. So we need a place with strongly mixed tides and a shallow place, a shallow embayment with a strong tidal, with a large tidal range. That's where you'd probably expect to see that. I have an example of that I'll show you later. But can you think of any area where you'd have something like that? Where do you have mixed tides? The west coast of the U.S., right? So can you think of a shallow system where you have a large tidal range? On the west coast, you probably have to go south of the border and find them. That's where the example comes from. So we'll talk about that later. And finally, the interaction of the M2 with the O1, which is the lunar diurnal, 25.82 hours. When the semidiurnal interacts with the O1, interestingly, it produces the K1, a modulation that's equivalent to the K1, 0.99 days. So that will reinforce the diurnal signal, and it generates these overtides of around 8 hours. So all these semidiurnal interacting with nonlinearly with the diurnal will generate distortions of around 8 hours. Okay? So that in mixed tides regimes, you should expect to see a strong signal at the 8-hour period, at the third diurnal frequency, because of the nonlinear interaction between semidiurnal and diurnal. And then you have these other interesting ones of 5 hours and 3.5 hours. These two are similar, the 7 cycles per day, and also these two, 5 cycles per day. Okay? So let's take a break right now, and we'll come back to see what the implications of this table are. Can we buy fingers?
Yeah, your eye told me that some that you had were here, were in the lab.
Right. I don't know where they are. He knows where they are.
Yeah.
He said that he was going to put them away.
Okay. Should I use those? Or it doesn't matter?
Yeah. Maybe less now because it's going to be a relatively short program.
Maybe less.
First time.
More.
2 weeks. Remember, it can't be one this time.
Yeah.
We're going to run out of memory.
Yeah.
Maybe, well, you don't need more than, well, I think we can go up to 20 days, but 15 days.
Okay.
Because in 20 liters of water, the largest file was 750 megabytes. So that involved many more cells. Not many more. How many cells did you
18 and 32.
32 for the thickness.
Yeah, it's 8 meters times 4.
Right, so because I think we had a 25 in the other one. And, if you want to deploy for more than 15 days, we can make some.
Yeah, no, that's fine. 15 minutes.
Okay. 15 days with it. I don't know if they don't want to if they're uncomfortable with us using the finger, so let's use it.
Okay. That's cool. Everyone is cooking this. Trade, yeah.
Go away.
The spectra that you sent to me include beams outside the water, no? Right. But look where the depth is. You see where the good data stop. So I think some of those things are in the air. But what's interesting is that in one of them that we set, you can see sort of a diurnal signal above the water, so that must be the seafood.
I removed the surface.
Surface?
Yeah, so I just 17. The survey
So the-
I removed the surface.
So the data that you sent to me are all good. All the day. Some of them.
The 18 is not good. I removed. The 17 has some bad data. I need to play.
Okay, we should see it afterwards. Here.
the United States for like 35 years.
Yeah.
He came to India and he started learning the wrong side of the I couldn't even fathom driving on the wrong side of the road. Me, it freaks me out when I'm driving on a one-lane road and I can take a left without having to wait for the light. I mean, I'll be right on that highway. That's what I do too, but I can take a late one. There's no beach. How do you get to this?
There's a beach. I live a block away from the beach.
There's a beach. It's just
If I showed you a picture of
Us
those
on the lake.
beaches, you wouldn't, except for the waves.
So you're only
really
allowed
see
to
that.
enjoy it like 5 days a year.
Guys, 3 months. 3 months.
Everybody can enjoy it in 5 days. Whole population.
So going back to this table, now you can see that I have some numbers here on this row and some labels here. So what they mean here is that here we are subtracting M2 minus M2 or M2 minus N2, M2 minus S2. So this gives us a zero frequency. So these are even, they're called even modulations, and these would be even distortions because we're adding 1 plus 1. In this, we have twice the M2 minus the M2 or whichever constituent, so it's twice one harmonic minus one harmonic, so it's 2 minus 1, which is 1. So these are odd numbered interactions. Here we have twice the M2 plus the next harmonic. So it's 2 plus 1, which is also an odd harmonic. And here we have 4 times the M2 minus the frequency of whatever constituent. So it's 4 minus 1. That's also an odd interaction. We'll see in a little later what this means, an even and odd interaction. You should even interactions, as you will see, will produce distortions that are asymmetric, and odd interactions will produce interactions that are symmetric. We'll see in a minute why. Or in a moment, not in a minute. And here on this row we have the mechanism that generates the interactions described there. So these 4 mechanisms, remember this is the continuity mechanism, the advective mechanism, and the 2 frictional mechanisms, bottom friction mechanisms, produce all these modulations and all these distortions. And then only bottom friction, this U times U, produce these odd interactions, which are those distortions and modulations. And again, we'll see what we mean by that in a moment. So I just want you to keep that in mind. But the main thing here is that the 4 mechanisms, 3 of which arise from this momentum equation. Again, 1 of them from here and 2 of them from here. So B arises from here, and C and D from here. A from the continuity equation. All of them generate this type of modulations and distortions. All right, so let's see what they look like. So the direct overtypes of the M2 look something like this. There's the M2 in blue, and the M4 is in orange. So you have, notice that this is is it an odd or an even harmonic? So if you go back to the table that we had before, let's go back. The M4 is even, right? So what that means is that it's always positive. What this happens is that the M4 will be generated it'll be maximum during the peak. Either, doesn't matter whether the peak is positive or negative. The M4 will always be positive. And then the M6 can have different shapes actually. The M6 can be 3 cycles here instead of 3 cycles like we have here. The M4 has 2 cycles. Imagine an M6 that has 3 cycles going from positive to negative. So it would look something like this. That would be an M6. But another M6 would be something like this. That here's 1 cycle, 2 and 3 cycles. The 1 cycle is very small here. And this M6, this shape, just arises from multiplying U, if U is a cosine of the M2, times the absolute value of the cosine of the M2. So you can generate this red line just by multiplying cosine of M2 times time times the absolute value of cosine of M2 times time. So going back again, if you look at this mechanism, the D mechanism, if you substitute U cosine of M2 times time in this expression, you get that red line. And again, you can do it just so that you understand it and you believe it. Alright, so if you make those interactions, so for example, M2 minus M4 will give you the orange line. Notice compared to the M2 unperturbed or not distorted. So the interaction of M2 minus M4 will give you this distortion, the orange line, which is an asymmetric distortion caused by an even harmonic. The harmonic is even, again because it's always positive, the M4. But when you subtract, and again you can do this with 2 waves, one with M2 frequency and one with M4 frequency, you generate this distortion when you subtract it. And as you see, it's an asymmetric distortion because over this side it's very small with 2 peaks, and over this side it's large with a 1 peak only. In contrast to the interaction of the M2 minus the M6, that produces a symmetric distortion because it's symmetric around 0. 2 peaks in the positive side, 2 peaks in the negative side, and it's caused by an odd harmonic. So again, going back, the M4 is an even harmonic, and the red line, the M6, is an odd harmonic because it can be positive or negative. And again, even harmonics will produce asymmetric distortions, and odd harmonics will produce symmetric distortions. So if you go to a place where you have strong nonlinear effects, you might observe a type that looks like that, like the red line or like the orange line. Those are possible shapes of the sea level or the currents in places of the world where you have strong nonlinear effects. And so the M2 will get distorted, and I insist the distortion can be symmetric, like the red line, or asymmetric, like the orange line. So there it is again, the animation of the rectified type. Now let me go back so that you see it again. Right, you see that it's not a sinusoid. And that shape, the light blue, the cyan shape, is caused by the interaction of the red line and the blue line. And the red line is semi-diurnal, and the blue line is a fourth diurnal signal. So that produced the distortion. Now this is a different distortion produced by semi-diurnal plus fourth diurnal plus sixth diurnal. So you can see that the flood is 1 peak and the ebb is 2 peaks. So the ebb is broader, so you have a strong distortion there, strong asymmetry. So again, you can play with different harmonics and you'll get different shapes. And this can happen in nature, like you can see in the observation there. Those are observed data. Those are currents near the surface from a place where there are strong nonlinear effects. Any guess of where this could be? I've shown you data from that area several times.
Mexico.
Sorry?
Somewhere in Mexico.
Somewhere in Chile, actually. It's in the, if it's not somewhere in Mexico, it has to be somewhere in Chile. This is a glacial fjord. Remember, the sill comes up it's a very shallow sill, very tall sill, that produces, the sill produces this very strong distortion. In this case, the positive current is ebb, and the negative is flood. So notice in particular here how you have two ebbs and two floods. These are observed data, so that's the flow interacting with the very sharp changes in bathymetry, producing very strong nonlinear interaction. And we were able to explain this actually with a nonlinear mechanism, just an incident wave plus a reflected wave at the sill that causes this type of distortion. But it causes large M2 and large M6 in this particular case. Okay, let's look at the physical explanation for what we've been talking about. So we talked about this at the beginning of class, that for long waves without friction, the wave propagates at the square root of GH. And these will be approximately constant throughout the tidal cycle only if the tidal amplitude eta is much smaller than h, like the example that we mentioned about the 100 meter water column. But if the ratio of eta over h is much smaller than 1, by that we mean maybe greater than 0.2, then we have nonlinear interaction. So in reality, eta over h in many estuaries is not much smaller than 1, and the wave crest will travel faster than the trough. This is for a progressive wave in shallow water. So that will produce, this is like the example of, which example in France that I showed you at the beginning of class? There you go. So you can see that this is not from Le Giron, but it's from somewhere else. And the blue line would be the tide at the entrance to the estuary. So that's the ocean tide, the blue one. And then this red tide would be at the head of the estuary. Notice how the tide goes down slowly because square root of GH is smaller, and it goes up very quickly because the square root of GH is large. So notice that it produces large asymmetries with respect to the ocean tide. So the difference between the sinusoid and these has an energy at the M4 frequency. And this is caused by this mechanism, the continuity mechanism. Now, from linear waves or linear theory, you can see that the current can be approximated as proportional to the phase speed of the gravity wave, and the proportionality ratio is the ratio between the tidal current amplitude and the depth of the water column. Again, that comes from this continuity equation, that momentum equation, which gives these two, so the solution is to these two differential equations is this. And if you substitute u over here and then integrate, you get this relationship. So using these two equations in the solution, you get this ratio. So I think we have talked about this, that this is a very powerful relationship in the sense that you can estimate the tidal currents that you will observe in a system just by knowing the tidal amplitude and the depth of the water column. Remember, this is for a linear wave, so it's an estimate, it's an approximation. So what happens is that if eta over h is greater than 0.1 of u, of 0.1, then u is not negligible with respect to the phase speed of the tidal current, as it usually is. Is that true? So say for let's think of an estuary 10 meters deep. What's the phase speed of a tidal wave? in an estuary 10 meters deep. 10 meters per second. And what's the tidal current speed? What would be a typical tidal current speed? 1 meter per second. So that's 1/10 of the U will be this U will be 1/10 of C. Right? So imagine if the depth starts getting shallower and the tidal currents are still strong, then the tidal currents are not small anymore as compared to the phase speed of the tidal wave. So the wave propagation velocity will be distorted because the wave propagation velocity at the crest will be the phase speed plus the tidal current. And at the trough, the wave will propagate as C minus the tidal current. So you can start seeing stronger asymmetries. So this results in a distorted wave profile, the tidal wave interacting with the tidal current. In this example, you have the blue line is the tide close to the ocean. Positive is ebb and negative is flood. And the orange one is further into the estuary. Notice how the orange line is strongly distorted. The blue line is slightly distorted, but it's close to being symmetric. But look at the orange line. The orange line gets a shoulder here, and then here it also gets sort of flat for a while. And again, during ebb, you get this shoulder, and then sort of flat here. So a strong distortion as you move in and out. And what happens is, during ebb, you have C minus U naught that causes this to suppress the tidal current during those stages. And then during flood, you get this flattening because the tidal current and the phase propagation interact with each other. So this is an asymmetric distortion produced by the inertial term mechanism. Now let's look at the two mechanisms that arise from bottom friction. So we can look at this. This is frictional loss of momentum per unit volume. Right here, frictional loss of momentum per unit volume. And it's greater at the trough than at the crest. Why is that? Why do you think it's greater at the trough than at the crest? The water column is smaller, so the friction acts more effectively throughout the water column than when the tide is high. Right, so the frictional loss of momentum is asymmetric. It's more during ebb than during flood. But also it can be symmetric because, well, we'll see that in a minute. I'm getting ahead of myself. So in the case that we have more loss of momentum at the trough than at the crest, then the crest will travel faster than the trough, and this will generate asymmetric distortions. That's what we said, that there's more frictional loss during ebb than during flood, so that's an asymmetric distortion, and it'll cause even harmonics. It'll cause M4. But also, that the interaction of U and the absolute value of U from this term, from the frictional term, can cause a symmetric distortion because there's maximum attenuation at maximum flood and at maximum ebb. So during maximum current, you get strong attenuation, and that could be regarded as a symmetric effect. So, and there's minimum attenuation at slack water or no attenuation at all. So this generates the M6, not harmonic. So we have asymmetric and symmetric effects. The asymmetric effects come from those three mechanisms. From the continuity or mass conservation mechanism, we have an asymmetric effect from the fact that the tidal wave will travel faster during flood than during ebb. The inertial mechanism, the advective mechanism that will cause the flow to be distorted differently during flood than during ebb. And also from the frictional loss of momentum per unit volume, which is one of the terms that comes from the frictional term here. This term will cause less frictional loss during flood and more frictional loss during F because it's shallower. And so those are asymmetric. The symmetric effect comes from U times U because you have extreme attenuation at flood and F and minimum attenuation at slack waters. So again, these symmetric effects produce odd harmonics, that is the M6, like the M6, because there are 3 slack waters and 2 current maxima in one period. So that's why you have an odd harmonic being generated, which is the M6, whereas the others are even. Okay, so that's the tide interacting with itself. Now, what happens when the tide interacts with the mean flow, like a river flow? So close to the place where the river comes into the estuary, there could be further distortion, and they can be explained in terms of the changes in the phase speed of the tidal wave, and in terms of frictional attenuation too. So the mean river flow makes the F current stronger, right, because it tries to go out, which means that there is increased frictional loss because the currents are stronger. And the flood current's weaker because it's opposing, the river is opposing the tidal flow. So if the currents decrease during flood, then you have a decreased frictional loss. So that's an asymmetric effect. Greater energy loss than if the river flows were not present. This translates into reduced tidal range and greater damping of the tidal wave. So this again, the example that I had shown before, where the elevation, the mean elevation is here. But what happens when you have a river, then the mean elevation will go up. So you have greatest attenuation here during ebb, weak attenuation during flood. This is when the river flow is still weaker than the tidal flow. So this will generate asymmetric effects because you have, these effects are asymmetric from what happens during flood. The generation of M4. And you will still have symmetric effects that will produce M6 because you will have strong attenuation here, strong attenuation here, strong attenuation here, strong attenuation here. So you do have frictional generation, although it's asymmetric. So you will have the generation of M6 as long as the river velocity is smaller than the tidal current velocity. So what that looks like is something like that. The generation of this will generate an M6 distortion. If you plot attenuation, energy attenuation versus time, during ebb you're going to have more, that is during this period you're going to have more attenuation. During flood it's going to be weak, during ebb strong, during flood weak. It said that it's symmetric because you have the maximum occurs, the maximum attenuation occurs during maximum current, even though in magnitude is asymmetric. So now, when the river flow is greater than the tidal flow, the flow becomes unidirectional. You see a tidal signal, but still everything is going in the ebb direction. So you don't have any generation of odd harmonics like the M6 because you don't have slack waters anymore. And since you're not going to have slack waters, you're not going to have a flood period, and you won't have attenuation during flood periods. What's going to happen is that the minimum attenuation will happen at these times, at the times of maximum flood. Instead of having maximum attenuation as we did when there's no river or when the river discharge is weak, now we're not going to have any attenuation during flood. I mean, it's going to be the smallest, the minimum attenuation. So if you plot attenuation now, it has an M4 shape. If you go back, this is an M6 shape, and this is an M4 shape. Okay, so now let's look at some examples with real data. This is a spectrum for two flow components of the current velocity at the entrance to Chesapeake Bay. Almost 6 months of data. So who can interpret that spectrum? Who can describe it? What can you tell me about that spectrum? It says here normal spectral energy. So what happened is that the spectrum was divided by the maximum value. so that anything below this line, not by the maximum, yes, by the maximum, anything below this line is not significant. So who can describe this? Okay, we'll wait here.
Like 2 and 4 and 6. And then there's like a, for the north south Dakota, there's a 2MK something. Yeah, that one.
2MK5?
Yeah, 5. For just the north south.
Yeah, but let's go by parts. Huh? What does that mean? The greatest variability of the tidal currents are produced by the semi-diurnal harmonic. Right? You have also a lot of energy in the diurnal component. What does this mean? What do you think it means? Huh? I think you said it.
It's just waves.
Waves? What kind of waves?
Range waves.
Yeah, with what frequency? Come on, guys, wake up, because this is something essential that you need to, maybe you don't want to answer because it's a simple question. But this is something that you need to understand. If you're going to graduate from a coastal program, you need to know what we're seeing there. Yeah, these are low frequency variations. So this would be produced by atmospheric forcing. So anything that's to the left of here would be produced by atmospheric forcing. Well, actually, you might have some modulation of the tides here. So some of these would be fortnightly variation and monthly variation. So you'd have the 14.8 day period there and the 27.3 period somewhere there. So you have this is diurnal, semi-diurnal. But the main thing that we're talking about today is this thing. So what would you say about those peaks that you see in the high frequency?
M4 is the strongest.
That's right. M4 is the largest overtide. But you also have overtide. If we only had M2, we would only have this peak, M2, M4, and M6. If we had nonlinear interactions, M2, M4, and M6. But we have that the diurnal is large, so the interaction between these two, the nonlinear interaction generates this, the 2MK3, and the 2MK5 also.
So it only does, it's just, like, point of that, it would say it's only affecting the north-south component.
Right, for in the 2MK5. So you can make something out of that, or you can just say that it's pretty small, and it doesn't. And the main overtide is M4, and also you have this one that arises from the interaction between these two. If you remember, this 2MK3 is also, I think I have here, 2MK3 has it's 2MK5, 8 hours. No, this one. This one is similar to the MK3 also. So these are both the 2MK3 and the MK3. That they have 8-hour periods. Right? So here's another example. Okay. I'm going to show you a Ponce de Leon inlet so that you feel more at home. What do you expect to see in Ponce de Leon inlet? Something like that, or how would it be modified in Ponce de Leon inlet? Any suggestions? Any surprises? You want to see a surprise? Any guesses?
Yeah, M6 is like that. I remember correctly.
Probably, right? M6 should be. We'll see. I'm going to show you currents from one bin of the ADC, from one being of an ADCP that was deployed, in December, around here, close to that point. You see the point? So there's the spectrum. Notice that I didn't label the frequencies this time. Because now I want you to tell me for sure. So it's very interesting, right? You have this. Well, I'm not going to say anything.
Interaction with K1 and K2 could be relatively informal.
The interaction between these two, you say it's weak?
Relative compared to informal.
That's for sure. And you have, this is what? Right. Notice we talked about the 7 cycles per day. Which one was it? This one. I don't know if it's this one, what we're looking at there, or it could also be this one. No, not that one. 3.5. Either of these two. This one. And then we have this other one. Where do you think this would come from? These two are sort of first generation daughters of the M2. And this M8 is the second generation. So it's a granddaughter of the M2. So it's generated from either of these two interacting. I think, well, I need to look into that, but it's very interesting that you have this M8 there. So you have very strong nonlinear effects there. Another example now that I was mentioning before, shallow embayment with mixed tides. So we go to the Gulf of California. There's the Baja California Peninsula. And there's a relatively small embayment there. Where's my arrow? There. Small embayment. And I'm going to show you data from a Moore instrument here. There's the maximum depth around 7 or 8 meters. You can see very complicated depth, but this channel is around 1 kilometer wide. And this channel is connecting the embayment to a small embayment to the big embayment. So that's this channel. This channel. That's connecting this big embayment to the small embayment there. So 7 meters of water, the tidal range, I think 1.5 meters. So expect long, strong nonlinear interactions. And here now we're looking at the spectral amplitude, contours of spectral amplitude as a function of depth and time, frequency and depth. So what I did is I calculated the spectrum for each depth, each being of the ADCP, and calculated here the contours of the spectral amplitude. So red means high spectral energy at that frequency and at that depth. So you can see that there's very weak depth dependence of these. So this is a barotropic tide that's being distorted. And you see all the harmonics generated there. Just like we see in Ponce de Leon. Right, we see the M4 and M6. We see also these ones, the third diurnal and fifth diurnal. We see the seventh diurnal also. And that's because, again, this one, and this one arise from the interaction of these two. And the M4 and M6 arise from the interaction. Notice here that in Ponce de Leon, the M4 and M6 were large. And here, the ones arising from this interaction are larger than the M4. Well, this one is larger than the M4. and that's because it's the tide is strongly mixed, close to being dominated by a diurnal constituent. So here it's more semi-diurnal. It's slightly mixed, but semi-diurnal, and here it's mixed also. And the final example comes also from the glacial fjord. Had I shown you this photograph before? Okay, we got a time series at that glacial fjord before. Up to now, I've shown you data from towed ADCP. And I told you that this is in a remote area in Strait of Magellan. You have to sail for 8 hours to get to the spot. So there's nothing nearby, no human influence nearby. The closest one would be perhaps 3 or 4 hours. And we took that frame to deploy it on the bottom with the ADCP pointing upward. And then by the time came for us to sail, they couldn't find any divers that were willing to do the job. So we had to improvise and use the same frame, but now floating at the surface with those floats, and pointing the ADCP now downward instead of having it on the bottom pointing upward. We had to improvise like that. And we tied this frame with 3 lines and heavy weights to the bottom, so it had some excursion with the tidal currents, but at least we were able to get data. And this was deployed just seaward of the very shallow seal. So those currents that I showed you before that showed two highs and 2 lows, that comes from that, the top pin of this. But then if you do the spectrum as a function of depth, you get that. So you have depth and frequency here. So what do you see there?
M2 and 6.
Huh?
M2 and 6.
Yeah, you see M2 and 6 and M6. But strong depth dependence, right? Look at the M6 only appears in a very thin layer near the surface. So there's no M6 below the depth, below the minimum depth of the seal. So other than the seal, there's no generation of M6. That M6 is generated, as I was saying, or we think is generated by an internal tide that is reflected at the seal. So as the tide comes in, it gets reflected at the seal, and it generates that M6 only at the surface. If we were to go further away from the seal, we might see this signal further in the water column, because this internal tides propagate throughout the water column, like any wave race, down and up and down and up. And you see the semi-diurnal also is strongly depth dependent, and that's again because the current becomes intensified at the surface as it goes through the shallow waters of the seal. So this is a Bernoulli effect. Yep. So this allowed us to gain some understanding of what was going on. This representation of the spectrum as a function of spectra at different depths let us see that the distortion of the tide only occurred at the surface. So that's something that is not frequent to observe, because most of the times the distortions happen in shallow waters, and those shallow waters are influenced strongly by the tide throughout the water column. Just like the previous example in Mexico that you saw, that these the peaks were depth independent, same throughout the water column. Here it's quite different. Okay. Anything that you